Hello everybody, and welcome to Callum Cymru revision sessions. The session this evening will focus on physics at GCSE level and will be presented by Mr. James Ridd from Cynfig Comprehensive School in Bridgend. The session will last 45 minutes, where James Ridd will run through past paper questions on types of radiation and half-life. If you have any questions during the session, please use the question and answer section and we'll do our best to answer your questions. Please leave your name and email if you are interested to receive more information on future events. And today's session will be recorded, and the recording and any relevant resources will be uploaded to the e-sgol website under the Callum Cymru tab. Thank you, James Ridd. Over to you.
Oh, brilliant. Thank you for the introduction, Jane. We, as was advertised, are going to be going through types of radiation and half-life past paper questions. Now, if you would like to have a review of those topics in terms of the content, then I advise you to go to the Callum Cymru website and look and go through the relevant links and navigate to the previous video which we completed, which was, as I said, just on the theory. So good place to stop. But after you've looked at that and, providing you've had a good sort of grounding in that physics, then this is going to be a really good place for you to visit, because we're going to be going through the real a lot of the past paper questions today, well, as many as we can. So I'm not going to waste any more time. We are going to dive straight in. So first of all, then, we're going to start off by looking at a question which really calls upon some basic knowledge and understanding of, first of all, atomic structure. So in this question, we're asked to, it says the radioactive carbon-14 is an isotope of carbon. It is produced high in the atmosphere when a neutron combines with a nitrogen nucleus, releasing a proton in the process. So it says carbon-14 written in the form XZA, where Z is the proton or atomic number. A is often referred to as the nucleon or mass number. Can be written as carbon-614. So just as a little bit of revision for us, remember, this is the symbol. That's the carbon part. The bottom number is the atomic number, and the top number is the nucleon number. So write carbon-12 in the form AZX. So this carbon-12 bit, whenever you see the 12 refers to the nucleon number or the top number. The other thing which is really important here is to note that if it is carbon, then it must also have the same atomic number as given above. They will never expect you to know the atomic number. That's not required. So you do need to know, however, that if it is carbon, then it must have 6. So we know we're going to have 6 protons, or the atomic number is going to be 6. The symbol is going to be the same. Now, top number there is going to be 12. This, as I said, refers to the nucleon number. The nuclear reaction that produces carbon-14 is written below. So here we've got the notation for the neutron plus the nitrogen nucleus to give us the carbon-14 plus some other particle here. Okay. What we need to do with this is really balancing nuclear equations. That will be this topic here. Okay. So to balance a nuclear equation, you've just got to simply think of this arrow as an equal sign in the middle, and understand that the nucleon numbers on top on both sides must equal. So for example, here, if I count up my nucleon numbers, I've got 14 plus 1 gives me 15 on this side in terms of my nucleon number, and that must equal 15 on this side. So this number here must also be 14, because your 14 plus your 1 gives you the 15. The numbers on the bottom, however, slightly different. So on this side, if I count up the atomic numbers, I've got 7 plus 0, so essentially I've got 7 on the left-hand side. This side is equal to 7. And on the right-hand side, then, I've got 6 plus something. Well, that's got to be 1. So 6 plus 1 is going to give me our 7 on this side. So these two sides are balanced now. So that's one example of balanced nuclear equations. We've got another one coming shortly, just to make sure we understand what we're doing. Part C, complete the following sentences with the number of particles, if any, in a carbon-14 nucleus. So a carbon-14 nucleus contains how many protons? Well, as we previously discussed, that is the bottom number, so that's going to be 6 protons. How many neutrons? Well, here's the trick with neutrons. We know the nucleon number, the number on the top, is 14. That number represents the total number of protons plus neutrons. So if I have 14 protons plus neutrons, and of that 14, 6 of them are protons, then the difference there must be whatever we have left. Effectively, if we take the bottom number away from the top number, then we're going to end up with the number of neutrons, which in this case is 8. I mean, to provide an analogy that might help, if I said I have got 10 apples and oranges, that would be like the nucleon number. And if I told you 7 of them were apples, like the proton number, then you'd quite rightly tell me that the remaining 3 must be oranges. The bottom one here then, a carbon-14 nucleus contains, now this is almost like a trick question.
Can you move it up, please, so we can see?
Oh, I do apologize. Thank you.
It's okay.
So how many electrons does it contain? That is like a trick question. This is literally an examiner trying to catch you out here, because the nucleus, if we recall how a nucleus is constructed, is made up of protons and neutrons. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 nucleons. So that's 6 protons. I'll denote those with a little plus randomly. But of course, the electrons, if you remember, in terms of atomic structure, are in fact around the outside. So in this case, I'd have my 6 electrons. However, they would not be located in the nucleus. So it contains 0 electrons. So the atom contains 6 electrons, but the nucleus contains no electrons, okay? And that will have caught a lot of people out. So just be aware of that. That's examiners being just really mean people in general. Okay, so moving on. We've got another question here which I've selected for us, which draws upon some of the knowledge and some of the things we just learned in the previous question. It says isotopes of iodine can be used to study the thyroid gland in the body. This question, if you are interested in reading up on it, is to do with radioactive tracers. It's how we use radioactivity to provide us with medical images. A small amount of the radioactive isotope is injected into a patient, and the radiation is detected outside of the body. 2 isotopes that could be used are iodine 53123 and iodine 53131. Now again, you'll notice that they're both iodine because this number on the bottom is the same. The atomic number is the same. So answer the following questions in terms of the numbers of particles. What is one similarity between these two? Well, this is where you've got to know what the atomic number represents. And it's also referring specifically, look, to the nuclei. So we could say both have 53 protons. 53 protons. State one difference between the nuclei of these 2 iodine isotopes. Well, the difference here is not enough to say that the nucleon number is bigger, although that is certainly the case, or the mass number is bigger. We'd have to really be a bit more specific. So we could say that, I guess, iodine 1, 2, 3 has how many neutrons? Well, Remember from the previous question, we take the bottom number away from the top. So in this first instance, it would be 70 neutrons. And in the second instance, if I went to iodine 131 has, right, and then we're going to add on another 8, isn't it? So that's going to be 78 neutrons. All right. So moving on to the next part then. The nucleus of iodine 131 decays into xenon by giving out beta and gamma radiation. What is beta radiation? Now, this is to do with the characteristics of the 3 different types of radiation, alpha, beta, and gamma. So in your revision, you need to make sure that you're up to speed with those. Now, a beta particle is a fast moving electron. An alpha particle is a helium nucleus, and gamma radiation is just electromagnetic radiation. You also, as well, do need to know, as well as being able to state those terms, what they look like for higher tier for balancing nuclear equations as well. So complete the equation below to show the decay of iodine 131. So we've got our iodine nucleus here. It decays. Now, we said we're going to treat this a bit like an equal sign, and both sides have got a balance. So I'll start at the bottom this time. Doesn't really matter where you go, where you start off. 54 and something is going to give me 53. All right, okay, 54. Well, it's not going to be plus something, is it? It's going to be, in fact, minus 1. 54 minus 1 would give me 53. And then if I look at the top, the nuclear number here for the beta particle is 0. Therefore, for both of these sides to balance on top, we must have 131 on top. All right. Couple of important notes. First of all, the whole beta particle thing. This is the annotation for a beta particle, but similarly, as I previously mentioned, you may need to know the annotation for an alpha particle. Now, WJC tend to really use helium instead of writing the symbol for alpha, and a helium nucleus, which is what an alpha particle is, has the following notation. So you will need to know that for balancing nuclear equations. And then gamma radiation, well, you see it here, it has no mass and no charge. Therefore, it will not have any numbers. It won't have a nuclear number or an atomic number. But yeah, you're going to need to know these. Incidentally, the symbol for alpha, I mean, you could write it as this. All right. That is also acceptable. But generally speaking, WJC use the notation of He for helium. Okay. Right, part C then. Sorry, I'm just moving things around a little bit. The isotope iodine 123 decays by gamma emission. Explain why it is better to use the iodine 123 than 131 as a medical tracer. Now, this comes down to understanding a little bit about how medical tracers work and how tracers work in general. So you would inject a patient with a small amount of a radioactive tracer, then you would use a gamma camera or a radiation detector to locate an image in the body where that radioactive source has gone to. Now, in the top of the question, it says it's used, look, to study the thyroid gland, right? Tell you that. Now, if a person's thyroid gland is working correctly, then the iodine will be taken up by the thyroid gland. And when it's taken up by the thyroid gland, we'll see on a medical image, we'll see that there's a lot of radiation or gamma radiation being emitted at that spot. And then we will know that that person's thyroid gland is working correctly. Should it be the case, however, that the thyroid gland is not taking up iodine correctly, then we would see an absence of that gamma radiation at that point, and therefore we'd know that there was a deficiency of sorts there. The important thing here, though, is that we've got to decide between these two sources. Now, gamma, okay, would be the best, okay? So explain why it's better to use gamma emitter is better because it can penetrate, okay, outside the body or outside the body and be detected. Now, it is worth saying as well that with a beta emission, it is more ionizing. So it's better to use this one as it is even safer, all right, because you could even say that beta emitter is more dangerous and ionizing. Okay, let's move on. So this next one is to do with, again, now the properties of alpha, beta, and gamma radiation, and in particular, the penetrative power. We've just already discussed briefly that gamma radiation passes through the body, it can penetrate out of the body and be detected very easily. But you also need to know that, for example, alpha is stopped by something as thin as paper. So if we had an alpha source, oh, I shouldn't have drawn that, sorry. I didn't mean to draw a wave then, apologies. It would be stopped by something as thin as paper. Gamma would quite happily pass through paper and even aluminium and would be stopped by thick lead. And beta radiation quite happily passes through paper, or it passes through paper reasonably well, and then would be stopped by something like 3 centimeters of aluminium. So that's just a question purely related to penetrative power and the characteristics of those 3 types of radiation. It said continue each arrow, didn't it? As far as each type, that's fine. Maybe I should make it into an arrow. Who knows? Okay. Nice, easy one. Right, next. Right. So here we have a question which again is related to characteristics of alpha, beta, and gamma. So we're making it a little bit more complicated now than it was in the last question. So we've got a list of radioisotopes and their decay mode. Now, decay mode basically just refers to whether you emit alpha, beta, or gamma. So here, this is our alpha particle or our helium nucleus, okay? And then that stands for obviously our beta particle, which is a fast-moving electron. Now, here we've got beta and gamma, and then iodine 131 is just a gamma emitter, and then finally radium, which is alpha and gamma. The table below shows the count rate detected from 3 of the radioisotopes above when different absorbers are placed between the source and the counter. The distance between the counter and the radioisotope is fixed at 2 centimeters. Now, this question could have maybe had a part to it which sort of asked why this was important, but if you're going to compare different sources, then this distance of 2 centimeters being fixed would be in fact an important variable to keep the same. It would be a control variable. Just thought I'd mention that. So now we have our table and those different properties, and we're asked to identify radioisotope X. Now we've got to go to the table and look at those properties to properly identify it. So with no absorber in place, we have 21 counts. Then with paper blocking, we have 20 counts, which is virtually the same. Aluminium placed in front, 21. So again, unchanged. Now, there is some random fluctuation here, which we'd expect because radioactivity is a random process. And then finally, we've got lead. Now, when the lead absorber is placed in front, we see a significant drop to the count rate. So the isotope in question here clearly can't contain any alpha or beta radiation, because were it to do so, then we'd see a decrease when the paper absorber was placed in front due to alpha not being able to penetrate paper, and we'd see a further decrease if it were a beta emitter due to the aluminium source being placed in front and therefore stopping the beta particles. We see no change with paper and aluminium, so we can only conclude the radioisotope X contains only gamma radiation. So we've got here, we're looking for a source that contains only gamma radiation, and there it is again. Excuse me, iodine 131. So radioisotope X is iodine, iodine 131. And the reason, I think, in the interest of time, I'm gonna not write that out. But suffice to say that quite quickly, there is no change in the count rate from paper and aluminium, and there's only a change due to lead. So I want to get through as many questions as possible. Radioisotope Y. So let's apply the same kind of logic to figuring out what Y is then. Okay, so if we come up here, we look at Y. So the camera's gone a little this way. Y, we can see with no absorber 74, with paper, virtually no change. So with paper and virtually no change, that suggests that it didn't contain any alpha particles. But then when we put the aluminium absorber in front, we see there is a significant decrease. So we must conclude then that it contains beta particles because we see the significant decrease with aluminium. And then finally, we also see a further significant decrease, look, all right, when we go from aluminium to lead. So this again would suggest that we had a lot of gamma radiation passing through, and that in fact it's now gone down to 15, which tells us that this source would have contained both beta radiation and gamma radiation. And if we look at our table, the culprit there must be silver, okay? So it must be that one. So that's silver 110, silver 110. And again, the reasoning, I've just been through it and I've discussed it, so I'm not going to write the reasoning down. And if you want to pause the video and go back, by all means, look at it. But just quickly again, it's because there's a decrease for aluminium and a further decrease when lead is placed in front. Therefore, it must have contained those two. And then finally, radioisotope Z. Well, here, look, with radioisotope Z, when we put paper in front, we see a decrease. So the first part of our answer would be to think, right, okay, if there's a decrease when paper is placed in front, that must mean that it's an alpha source or it has alpha radiation. We see no change, virtually no change between paper and aluminium in the count rate, but then we see a further change when lead is placed in front. So again, what that must mean now is that the alpha particles are being stopped by paper, and of course they're being stopped by the aluminium. However, here we can still see there's gamma radiation getting through. And then finally, we see this reduction when the lead is placed in front, meaning that this source, or radioisotope Z, must contain both alpha and gamma. So this must be the famous radium-226. So that would be radium. And again, go back and have a little look. Right, moving on. Next question is to do with background radiation, which again we haven't discussed yet, but this is the radiation that's around us all the time. Quite commonly you see these pie charts popping up in questions, and here we can see the breakdown of the different sources of background radiation that are present in the UK today. The pie chart obviously represents the proportions of those sources. A single reading of the total background radiation showed 20 counts taken in a minute. All right, so a single reading of the background radiation showed 20 counts taken in a minute. Calculate the total number of counts per minute from cosmic rays and food and plants together. So let's see now. So we got to think, if the total, if you like, the whole pie is 20 counts per minute, it is saying what would be the contribution, really, calculate the total number of counts per minute from cosmic rays and food and plants together. So we'll go to our pie chart. We can see we've got cosmic rays and food and plants together. Now, if you look at this, really, this is quite conveniently, right, 25%. I've never seen a question where you've had to do maybe what you might have done in maths, where you are measuring an angle and working out what that proportion is of 360 degrees. Where I have seen questions like this in physics, it is always some easy amount. This case, 25% or a quarter. So a quarter of my 20 counts per minute are in fact from those sources. So that's just going to be 20 divided by 4, which is obviously 5. All right, 5. Describe how a more reliable value of the total background radiation could have been found. Well, a couple of important points here. Count rate could have been taken several times. And a mean average taken. Oh, it's the red. So that would be one way of improving the accuracy or the result, of making it more reliable. All right. And alternatively, you could have taken count rate over longer time. So in this case, they took it over 1 minute, we were told in this question. But were you to take the count rate maybe over a period of 20 minutes and then divide by 20 to get the counts per minute, you were more likely to get, well, you will get a more reliable result. The reason being that in any given minute, because radioactivity and radioactive decay is a random process, you can't really predict exactly how many you're going to get in a minute. But over the course of 20 minutes or, however long you decide to take it, a longer period at least, you'll find that those random variations will even out and you'll settle on a more reliable value. Also give the name of one source of background radiation that depends largely on the rocks in the area in which the measurement is taken. So in this case, it's calling on your knowledge of where radon gas comes from. Now, radon gas comes from rocks in the ground, and in particular, rocks, for example, which granite is a big source of radium, and radium decays into radon. So essentially, if you've got, I don't know, some rocks and you've got a lot of radium in those rocks, all right, then when radium decays, it decays into a gas, and then that gas is radon gas, which is still radioactive. So radium is radioactive, and the products of that decay, radon, are a gas, and they're also radioactive. Now, I'm going a little bit further here, and this will be on the video that supports this. As I mentioned before, the theory, radon features quite largely on here because it's a gas. It can be easily inhaled, so you have generally a higher exposure to radon than other sources. Right. Okay. Moving on. So next, then, we've got a question on. Are we going to do this question? Let's see. We're going to do the first part of this question, actually. I'm conscious of time, and I'm conscious of the fact that I really would like to go through some half-life questions as well. But we're going to talk about now how you deal with background radiation experimentally, which is a very important thing that pops up quite frequently. So a radiation detector is connected to a counter in a classroom. Absorbers were placed directly in front of the detector in an attempt to find which radiation was being given off by the radioactive source americium-241. The following results were obtained. The figures include the mean background radiation count of 20 counts per minute. Right, this is such an important piece of information. So it says the figures include the mean background radiation count of 20 counts per minute. So many students will have missed that. Now use the following information in the table above and your knowledge of radioactivity to answer the following questions. Calculate the mean number of counts per minute emitted by americium-241. Well, we know here we got 350 without any absorber placed in front. And we know that the background radiation count is 20. So we have to subtract the background radiation count of 20 to get the true value of 330. It's a bit like if I said to you, please, can you weigh out 300 grams of pasta, and I give you a bowl. Well, how would you go about doing that? Well, you would maybe weigh the pasta in the bowl. Then you would weigh the bowl and you take the weight of the bowl away from the pasta. It's exactly the same concept. We measure the amount of background radiation, which is in this case 20. We measure the total amount of radiation, which is 350. And then we have to remember to take that background radiation away from that total. So explain which type of radiation is given off by the source. Well, just quickly, just calling on what we learned before. Here we've got no absorber here, 350. Then we see when we have thin card placed in front as an absorber, there is a massive and significant decrease here. So that tells us that this must be an alpha source, because a beta would pass straight through and so would a gamma. We see very, very little change then when we go down to 3 millimeters of aluminium, other than random fluctuations. And then finally, we see a massive decrease again now down to 1, right, from aluminium to lead, which tells us that that decrease must have been caused by gamma. So we know we're dealing with a source that is going to be, is going to have those two in there. So I'm going to move on now with this question because a lot of the other bits are similar to bits we've done before. And like I said, we're conscious of time. We're going to talk now about half-life. And here, with half-life, we are told that the mass of a sample of radioactive isotope is 64 grams. It has a count rate of 800 counts per minute. It is a gamma emitter. A lot of information in that first sentence there. 800 counts per minute. It's a gamma emitter. It has a half-life of 30 minutes. Radioactive decay follows the pattern below. So half-life is quite simply the time it takes for half of a radioactive sample to decay, or for the activity, the amount of counts per minute, to go down by half also. So we've got original amount, after one half-life, half is the amount remaining is halved. And actually we can use this to help us answer the question. Find out how many half-lives it takes for the count rate to fall to 50 counts per minute. So we start off at 800. Now, after one half-life, we'll have gone to 400. That's going to be one half-life there. We'll have gone to 400. After two half-lives, it's going to half again. So we'll end up at 200. That's going to be two half-lives. Then after three half-lives, we'll have gone down to 100. That's 3. And then down to 50 at 4 half-lives. So the answer to this question, find out how many half-lives, not how long, how many half-lives. The answer is 4. How long does it take for the count rate to fall to 50 counts per minute? Now, this is how long does it take? All right, how long does it take? Now, we know how many half-lives it is. We worked that out just now. It's 4. So we know it's 4 half-lives. But how long is that in time? Well, if you look back at the start of the question, and if you're really struggling in an exam, just good exam technique, go back to the start of the question and start looking for information you might have missed or you might need later on. Sometimes you can be on part D, which is on another page, and the information you need to answer part D is right back at the start of the question. So we know that every half-life takes 30 minutes. And because every half-life takes 30 minutes, if we do 4 half-lives times 30, we end up with 120. Now, look at this unit. All right, it wants you to put a unit in here. You've got to get this right. This is 120 mins. It's 120 minutes. Similarly, we could have written, couldn't we, 2 hours. That would have also been fine. What mass of the radioactive isotope remains at this time? So we're going to do a similar kind of thing like we did at part AI. So we started off with a mass of 64. Said that at the top of the question, right at the top here. Then that's going to go to 32 after 1 half-life. Then it's going to go to 16 after 3 half-lives. Then it's going to go to 8. Oh, no, Sir's got that wrong, look. 1 half-life, 2 half-lives, 3 half-lives. There's another one there, isn't there? So after 4 half-lives, the mass, rather confusingly, going to end up as 4 grams. Let's just check that again. 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Yeah, that's right. Explain why this radioactive isotope would be suitable as a radioactive tracer in medicine. Now, as well as, I'm going to talk this rather than write it, we've already previously answered this where we said that the gamma source is obviously the better choice because it penetrates out of the body and it can be detected. But also, very importantly here is this half-life question, this half-life here. Now, for a radioactive tracer to be very suitable, we needed to have a short half-life. And the reason for that is that were it to be a long half-life, it would be lingering around inside a person's body for a long period of time, emitting gamma radiation, and consequently, that could cause damage and put them at a higher risk of cancer. So having a short half-life means that within, in this case, maybe 6 half-lives, maybe 3 or 4 hours, that radioactive load, that exposure has gone right down. So that's the reason why. So a short half-life reduces the risk of radiation exposure to the patient. All right. Let's do another half-life question. Yes, this is a similar kind of question here to do with half-life, but it's also using another application of radioactivity, not as a medical tracer, but in this case as a treatment for cancer. All right, so we've got a table, got a lot of information here on half-life and method of decay. Using the information in the table, it says you select the most suitable radioisotopes for the task below. So for treating cancer by injecting the radioisotope directly into the tumor, that would be astatine, because it's an alpha source and therefore it's going to ionize the tumor itself without penetrating out into the rest of the body, and it's not going to linger in a person's body indefinitely for like 30 years or whatever. Okay, I'm going through this quickly now because there's one other half-life question I'd like to do. And then finally, to sterilize packaged surgical equipment. So if you want to sterilize packaged surgical equipment, you need it to penetrate through the packaging. So it's going to have to be something that's going to get through packaging and even through the instruments themselves to kill all the bacteria And then what are we going to choose for that? Well, the most penetrating one here is going to be, well, it's going to be beta or gamma maybe, or this beta source, which is quite penetrating. They have also both got a long half-life. Now, let's imagine we've got a machine that's going to sterilize surgical equipment. We do not want to have to replace the radioactive source in that every few hours because it's completely decayed and it's gone through a lot of half-lives, okay? What we want is something that's going to be an emitter for a long period of time, and it's something we're going to be able to use again and again and again without replacing. So it has to be quite penetrative. That's where the gamma and the beta come in. And in fact, gamma is really good at penetrating, so it will sterilize those surgical equipment, or those surgical tools rather. Moving on. Let's see. We're going to look for, conscious of time, we're going to look for a radioactive decay curve question, I think, which would be ideal. So we're going to jump straight to here. Okay. Right. A student does an experiment with dice to investigate radioactive decay. Now, you will either have done or you will be about to do this experiment where you will be taking some dice to model and, if you like, provide an analogy or simulate what radioactive decay is and how it works. Now, the dice represent radioactive atoms. They are thrown together on the floor. Those that show a 6 are removed. These represent atoms whose nuclei is decayed. The remaining dice, undecayed atoms, are thrown again, and the process is repeated several times. The student starts with 600 dice. Predict how many of the dice would show a 6 on the first throw. So the probability being 1 in 6 would be 600 divided by 6. That's going to be 100. Now that's what we would expect. But that's not necessarily what's going to happen, because remember, it's a random process. This is why it models quite well. So that's the most likely outcome, but certainly not the one that we can guarantee will happen. State why the student cannot predict which dice will throw or show a 6. And this is because it's a random process. It's a random process. You might have a table such as this, where we've got the results. So you've got the throw number here. We've got the number of 6s, and then we've got the number of dice remaining. You can see the pattern here, okay? So we start off with 600 dice. We throw 95 6s, and then we're left, of course, with 505. Top tip, whenever you see a table and there are blanks, look for a pattern. And this doesn't just apply to radioactivity and half-life. Virtually any table, if you're stuck, look for a pattern. So 505, you take away 85, you're left with 420. All right, so the point is this: I have 420, it goes down to 350, so that must have mean that 76s were rolled. All right, and then just to finish off, I'm going to do a little bit of a Blue Peter here, actually, because you wouldn't even know what that means, but that's fine. Okay, it's just a here's one I made earlier kind of job. So I plotted these results as was asked. We're just going to zoom out a little bit here. All right, we plotted the results as was asked at the top of this question. Really important point in physics and in science. Okay, we do not connect the points. We draw smooth curves where appropriate. So this here, as you can see, the way the points are going, and all half-life curves are smooth curves. If the points are indicating a straight line in direct proportionality, then you draw a straight line at best fit, but in no circumstances should you feel inclined to just connect the dots. If they do naturally connect, then fine, but it's straight lines or smooth curves and nothing in between. So here I've drawn my half-life decay curve, or my dice decay curve, and it says draw lines onto your graph to enable you to find the half-life of the dice. Now, to do that, I recommend a dotted line. How are we going to find half-life? Well, we start off at 600, and after one half-life, 300 will remain. So then we come across from 300, like I've done here, and then down, and that turns out to be about 3.8. Now, you can either write 3.8 here or 4. No, Jane will know for certain, but I think that's correct. You can write 3.8 there and still get the mark, I believe, okay? Because you can't exactly have 3.8 throws. It's 4 throws, but you'll be okay with either. So that is how it's shown. And incidentally as well, importantly, if you were to, for example, look at 2 half-lives, that would be, of course, when it goes from 300 down to 150, what you'd find is that, in fact, that time period is exactly the same. So the time it takes to go from 600 to 300 is the same amount of time as it takes to go from 300 to 150, as indicated here. And I think I'll just finish this little question and then we'll call it a day, I think. Yes, just this last one then. So there's ticks in the boxes that correctly give the meaning of the half-life of a radioactive substance. So for this, we've got the time taken for radioactivity to half. That's really sneaky, because if it had said activity, then that would have been okay, but that's just nasty, but that's wrong. The time taken for atoms to split in half, no, that's not what it means, that's wrong. The time taken for the number of undecayed particles to halve, yes, that's correct. And then the time taken for the count rate to half, that is also correct. So it's the time it takes for the sample or the mass or the mass of the radioisotopes or the number of radioisotopes to go down by half. That's true. And it's also the time taken for the count rate or the activity to go down by half as well. And then we've got a graph showing the decay curve of a substance. And we'll just do this one quick. Use the information from the graph on page 6 to write down the count rate after 100 days. So after 100 days, if we look at this here, we go to the time in days. We'd follow that up with a ruler, preferably. Mr. Rid's gone rogue here. All right. We indicate that we know what we're doing by showing the dotted line. We come across here, the count rate would be 400. So the answer to that first part there would be, in fact, 400. Write down the half-life of this radioactive substance. So the half-life is the time it takes to go down by half. And look how sneaky this is, because if it starts at 800, the time it takes to go down by half, well, it's going to go from 800 to 400, and we just worked that out. That took 100 days. So the half-life, it goes from 800 to 400, and that takes 100 days. So that is going to be 100. And then this one here, write down the time it would take for the count rate to fall from 50 to 25. Now notice that to go from 50 to 25, well, 25 is half of 50. And if it's half of 50, then that means it's gone down by half. So the time would be exactly the same. It's going to be 100 days. And the very last one, and we're going to call it to a close then, draw a decay curve on the grid below for a radioactive substance that has a starting count rate of 800 counts per minute, but a shorter half-life than the one shown. All right. So if it's going to have a shorter half-life, it's going to decay faster. And to indicate that, we're going to do a steeper line. So look, you're not going to be able to draw curves as well as me. All right. Just so don't beat yourself up about it. I'm like the best. Okay. And that is going to indicate, of course, that we've got a shorter half-life, because, again, if you came across here, look, it would be a shorter amount of time. All right. Now, let me just pop myself back on so I can say goodbye. I hope that we got a lot of past paper practice in there, which is what we were aiming for. So again, look at the theory in the video on Carl Cymru, which is on this very subject. So radioactive types of radiation and half-life. And you know, that will give you the background for the theory, and then the past paper practice, you put those two things together and it's a recipe for success. So thank you everyone.
Thank you, James Rid. I hope you all found today's session useful. And next week's session, at the same time, we'll focus on practical terminology and skills at GCSE level. So some of the things that James covered, we will cover and go into more depth. Thank you and goodbye.